A lithium-ion battery, known simply as Li-ion battery, functions as a rechargeable power source that leverages the reversible intercalation process of Li plus ions into electrically conductive solids to store energy effectively. Li-ion batteries distinguish themselves by offering higher specific energy, energy density, and energy efficiency, along with an extended cycle life and calendar life compared to other rechargeable battery variants. Noteworthy is the significant advancement in lithium-ion battery characteristics following their entrance into the market back in 1991. In the subsequent 3 decades, their volumetric energy density tripled while their cost plummeted tenfold. By late 2024, the global demand for Li-ion batteries had surpassed 1 terawatt-hour annually, with production capacity exceeding twice that amount. In the 1970s, M. Stanley Whittingham introduced the concept of intercalation electrodes and developed the initial rechargeable lithium-ion battery utilizing a titanium disulfide cathode and a lithium-aluminum anode, albeit encountering safety issues and remaining unreleased commercially. Building upon Whittingham's work, John Goodenough in 1980 integrated lithium cobalt oxide as a cathode into the battery design. The pivotal moment arrived in 1985 when Akira Yoshino devised the first prototype of the contemporary Li-ion battery, employing a carbonaceous anode instead of lithium metal. This innovation transitioned into commercialization in 1991 through a collaborative effort between Sony and Asahi Kasei, steered by Yoshio Nishi. The groundbreaking contributions of Whittingham, Goodenough, and Yoshino in the advancement of lithium-ion batteries culminated in their joint reception of the 2019 Nobel Prize in Chemistry. Lithium-ion batteries pose a threat of fire or explosion due to their flammable electrolytes, although efforts have been made to enhance safety in their development and production. To address this issue, lithium-ion solid-state batteries are under development to remove the flammable electrolyte component. Recycling batteries can lead to the creation of hazardous waste, containing toxic metals and posing a fire hazard. Challenges also arise in mining lithium and other minerals, particularly in water-intensive processes in arid regions. Additionally, certain minerals used in lithium-ion chemistries, like cobalt, can be classified as conflict minerals. In response to environmental concerns, researchers strive to enhance mineral utilization efficiency and explore alternatives such as lithium iron phosphate batteries or non-lithium-based options like sodium-ion and iron-air batteries. The term Li-ion battery encompasses a range of approximately 12 different chemistries, each with its own characteristics. Manufacturers can tailor lithium-ion cells to prioritize either energy density or power density. For instance, handheld electronic devices commonly utilize lithium polymer batteries with a polymer gel electrolyte, a lithium cobalt oxide cathode, and a graphite anode, delivering high energy density. Meanwhile, lithium iron phosphate, lithium manganese oxide, and lithium nickel manganese cobalt oxide chemistries offer extended battery life and increased discharge rates, making them advantageous for various applications. Lithium nickel, manganese cobalt oxide, and its variations are extensively utilized in electrifying transportation, playing a pivotal role in reducing greenhouse gas emissions from vehicles when combined with renewable energy sources. The demand for safer, more efficient, and longer-lasting batteries is propelling innovation in battery technologies beyond traditional lithium-ion chemistries. Industry insights from Conseguic Business Intelligence suggest that upcoming battery technologies such as lithium-sulfur, solid-state, and lithium-metal variants are forecasted to gain substantial commercial acceptance. Research on rechargeable Li-ion batteries traces back to the 1960s, with one of the earliest instances being a QF2H Li battery conceived by NASA in 1965. The initial breakthrough leading to the modern Li-ion battery form occurred in 1974 by British chemist M. Stanley Whittingham, who implemented titanium disulfide, TiS2, as a cathode material due to its layered structure enabling lithium-ion absorption without altering its crystal makeup. However, Exxon faced challenges commercializing this design in the late 1970s due to the high cost and complexity of TiS2 synthesis, its sensitivity to moisture, and the hazardous gas hydrogen sulfide, H2S, released when exposed to water. The batteries were also prone to igniting spontaneously as a result of metallic lithium presence within the cells, causing Exxon to halt the development of Whittingham's lithium-titanium disulfide battery. In 1980, other researchers like Ned A. Godshall and Koichi Mizushima, along with John B. Goodenough, began exploring alternatives. They replaced TiS2 with lithium cobalt oxide, LiCoO2, known as LCO, offering a higher voltage and greater stability, though flammability persisted as an issue. A pivotal advancement in battery safety emerged when lithium metal anodes were replaced with intercalation anodes to prevent dendrite formation and short-circuiting. Jürgen Otto Basenhard showcased lithium-ion intercalation into graphite anodes in 1974, with later improvements by Rashid Yazami, using a solid organic electrolyte for enhanced stability. Akira Yoshino's discovery in 1985 saw the use of petroleum coke as an intercalation anode, offering structural stability that led to the creation of the first commercial lithium-ion battery. Yoshino's patented design featuring Goodenough's LiCoO2 as cathode gained traction, with Sony commencing production of rechargeable lithium-ion batteries in 1991, followed by a joint venture between Toshiba and Asahi Kasei Co., achieving the same the following year. Over the years, energy density enhancements were achieved by transitioning from soft carbon to hard carbon and eventually graphite for the anode. Advancements have continued with CATL's announcement in April 2023 of scaled-up production for a semi-solid condensed matter battery, showcasing a groundbreaking energy density of 500 by Czechik, with electrodes composed of a gelled material requiring fewer binding agents aimed at applications like battery-powered aircraft. A novel iteration of lithium-ion batteries involves flow batteries with redox-targeted solids, omitting binders and electron-conducting additives and enabling independent energy and power scalability. The negative electrode in a standard lithium-ion cell is commonly composed of graphite, while the positive electrode is typically a metal oxide or phosphate material. An organic solvent with a lithium salt serves as the electrolyte. To prevent short-circuiting, a separator keeps the negative, anode, and positive, cathode, electrodes apart. These electrodes link to the circuit through current collectors. During discharge, the negative electrode functions as the anode and the positive electrode as the cathode. However, colloquially, the negative electrode is usually referred to as the anode in battery design discussions, and the positive electrode as the cathode. In its fully lithiated state, graphite can achieve a theoretical capacity of 1,339 coulombs per gram. The positive electrode mainly consists of a layered oxide, a polyanion, or a spinel material. Experimental options like graphene-containing electrodes are not yet economically feasible due to their high cost. Since lithium reacts vigorously with water, a non-aqueous electrolyte is used, with the electrolyte salt typically being lithium hexafluorophosphate for its good conductivity and stability. Various salts like lithium perchlorate and lithium tetrafluoroborate are used in research, but are not suitable for larger cells due to compatibility issues. Copper with a nickel tab functions as the current collector at the negative electrode. Different designs and treatments for current collectors, such as foil, mesh, or coatings, can significantly impact the cell's voltage, energy density, lifespan, and safety. Research is focusing on nanotechnology to enhance performance, exploring nanoscale electrode materials and alternative structures. The reactants utilized in the electrochemical reactions within a lithium-ion cell consist of specific compounds housed within the electrodes, both containing lithium atoms. Despite a plethora of materials explored for application in lithium-ion batteries, only a handful are deemed viable for commercial use. Notably, all commercial Li-ion cells integrate intercalation compounds as active components. The negative electrode commonly features graphite, sometimes infused with silicon to augment capacity. As for the electrolyte, it typically comprises lithium hexafluorophosphate, dissolved in a blend of organic carbonates. Diverse materials are employed for the positive electrode, such as LiCoO2, LiFePO4, and lithium nickel manganese cobalt oxides. Throughout cell discharge, the negative electrode serves as the anode, while the positive electrode acts as the cathode. Electrons migrate from the anode to the cathode via the external circuit. An oxidation half reaction at the anode engenders positively charged lithium ions and negatively charged electrons. Concurrently, lithium ions traverse the electrolyte while electrons move through the external circuit towards the cathode to amalgamate with the cathode material in a reduction half reaction. The electrolyte furnishes a conductive medium for lithium ions without participating in the electrochemical reaction. The discharge reactions diminish the cell's chemical potential, transferring energy from the cell to where the electric current expends its power, primarily in the external circuit. Conversely, during charging, electrons flow from the positive electrode to the negative electrode via the external circuit. Charging necessitates the external circuit to supply electrical energy, which is then stored as chemical energy within the cell, albeit with some loss attributed to Coulombic efficiency falling below unity. Both electrodes enable the ingress and egress of lithium ions through their structures via a process termed insertion, intercalation, or extraction, deintercalation. As lithium ions oscillate between the two electrodes, these batteries are dubbed rocking chair batteries, or swing batteries. The cited equations showcase the chemistry involved, delineating the reactions during discharge and charge, showcasing the intricate mechanisms at play within lithium-ion cells. In the 1980s, Manthiram discovered that oxoanions like molybdates and tungstates could significantly raise the redox potential of metal ions in comparison to oxides. Despite offering better stability and safety than oxides, oxoanionic cathode materials face challenges due to poor electronic conductivity caused by the distance between metal centers, slowing down electron transport. To mitigate this, cathode particles smaller than 200 nanometers were utilized, each coated with a layer of electronically conducting carbon. This practice, however, decreased the packing density of these materials. While various combinations of oxoanions, such as sulfate, phosphate, and silicate, with metals like Mn, Fe, Co, and Ni had been explored, LiFePO4 emerged as the only commercially successful option. Initially favored for stationary energy storage due to its lower energy density compared to layered oxides, LiFePO4 gradually gained popularity in electric vehicles post-2020. The positive electrode technology has seen major producers including Ronbay Technology, eSpring, EcoPro, Umicore, LNF, and POSCO showcasing materials like lithium, nickel manganese cobalt oxide, NMC, lithium nickel cobalt aluminum oxide, NCA, lithium nickel cobalt manganese aluminum oxide, NCMA, lithium manganese oxide, LMO, lithium iron phosphate, LFP, and lithium cobalt oxide, LCO. Each material caters to specific applications, offering advantages such as good specific energy, specific power density, high energy density, improved long-term cycling stability, and faster charging. When it comes to anode technology, graphite is a commonly used material, followed by silicon-based materials that have gained traction in recent years. The choice of anode material plays a crucial role in determining the energy density and durability of lithium-ion batteries. While graphite remains dominant due to its low intercalation voltage and excellent performance, alternative materials like silicon offer higher capacities, albeit with challenges like volume expansion. Ongoing research focuses on enhancing the capacity and stability of anode materials for better battery performance. High-entropy metal oxide materials are also being explored as potential options for anodes to improve battery efficiency and longevity. Liquid electrolytes in lithium-ion batteries, such as LiPF6, LiBF4, or LiKLO4, dissolved in organic solvents like ethylene carbonate, dimethyl carbonate, and diethyl carbonate, function as conductive pathways enabling cations to move from negative to positive electrodes during discharge. At room temperature, these electrolytes typically exhibit conductivities around 10 mebisemism, which increase by 30 to 40% at 40 degrees and decrease slightly at 0 degrees. The combination of linear and cyclic carbonates like ethylene carbonate and dimethyl carbonate provides high conductivity and forms a solid electrolyte interface, SEI. While ethylene carbonate alone is not liquid at room temperature, the addition of substances like dimethyl carbonate allows it to function effectively. These organic solvents decompose on the negative electrodes during charging, forming a stable SEI that is electrically insulating, yet promotes significant ionic conductivity, thus acting as a solid electrolyte. Solid electrolyte interphase, SEI, plays a crucial role in preventing further electrolyte decomposition beyond the initial charge, allowing batteries to function optimally. Solid ceramic electrolytes have emerged as a promising advancement in battery technology, offering enhanced safety by eliminating the risk of leaks present in liquid electrolyte batteries. These solid ceramic electrolytes, including lithium superion conductors and perovskites, demonstrate high ionic conductivity, rivaling that of liquid electrolytes. By introducing additives in small concentrations, the properties of electrolytes can be tailored efficiently and economically to enhance specific characteristics. The introduction of polymer electrolytes, like those utilized in lithium polymer batteries, shows potential in minimizing dendrite formation and maintaining conductivity, contributing to improved battery performance and safety. Diffusion of ions in the electrolyte is a critical process affecting battery performance, with factors like diffusion coefficients and porosity influencing the movement of lithium ions within the electrolyte solution. Lithium-ion batteries exhibit various structural levels, with small batteries comprising individual cells. Larger batteries interconnect cells in parallel within a module, and link modules both in series and parallel to form a pack. Packs can then be connected in series to elevate the voltage. To ensure safety, batteries may integrate temperature sensors, heating, cooling systems, voltage regulator circuits, voltage taps, and charge state monitors to mitigate risks like overheating and short-circuiting. On a macrostructural level, the majority of commercial lithium-ion batteries consist of foil current collectors, aluminum for the cathode, and copper for the anode. Anodes are typically made of copper as lithium does not alloy with it, while cathodes utilize aluminum due to its passivating properties in LiPF6 electrolytes. Li-ion cells exist in various form factors, divided into coin cells, small cylindrical cells, large cylindrical cells, and flat or pouch cells. Coin cells encased in stainless steel find use in devices such as hand watches, portable calculators, and research purposes. The cylindrical cells, common in e-bikes, electric vehicles, and older laptops, are structured without terminals. These come in standard sizes. The flatter pouch-shaped cells found in cell phones and newer laptops are known as lithium-ion polymer batteries. Cylindrical cells are typically produced in a Swiss roll configuration, enclosed in a container, allowing for faster manufacturing. Pouch cells, having the highest gravimetric energy density, lack a case but are required to be contained in certain applications to prevent expansion at high state of charge levels for stability. In current electric vehicles, 3 primary battery types are utilized: cylindrical cells like those in Tesla vehicles, prismatic pouch cells like those from LG, and prismatic can cells from manufacturers like LG, Samsung, and Panasonic. Moreover, developments in lithium-ion flow batteries have shown promise by suspending cathode or anode material in aqueous or organic solutions. As of 2014, the smallest Li-ion cell had a pin shape with a 3.5 mm diameter, weighing 0.6 Dre, created by Panasonic. Li-ion batteries with a coin cell form factor, often denoted with a Li-R prefix, are constructed mainly with LiCO2 cells. When considering cell voltage, LCO chemistry with hard carbon cathodes averages 3.6 VA. This figure increases to 3.7 VA when using graphite cathodes, providing a flatter discharge voltage curve. These versatile batteries find extensive applications in consumer electronics, toys, power tools, and electric vehicles. Furthermore, they play a role in niche areas such as backup power for telecommunications and are of interest for grid energy storage, despite not yet being cost competitive at scale as of 2020. Notably, some submarines have incorporated the use of lithium-ion batteries for their operations. Lithium-ion batteries exhibit varying energy density and voltage levels due to the diverse materials used in their positive and negative electrodes. The open circuit voltage surpasses that of aqueous batteries, affecting internal resistance, which rises with cycling and age, particularly influenced by storage conditions like voltage and temperature. As internal resistance increases, terminal voltage decreases under load, limiting the maximum current draw and leading to potential overheating issues. Batteries employing lithium iron phosphate, positive and graphite negative electrodes typically have a 3.2 V nominal open circuit voltage and 3.6 V charging voltage, while lithium nickel manganese cobalt oxide positives with graphite negatives boast a 3.7 V nominal voltage and 4.2 V maximum charging voltage. Charging is commonly executed at a constant voltage with current limiting features until reaching 4.2 V, followed by a constant voltage phase until current diminishes. Current generation lithium-ion cells have significantly reduced charging times, with some demonstrating fast charging capabilities like a 600 mAh battery, reaching 68% capacity in 2 minutes, and a 3000 mAh battery achieving 48% capacity in 5 minutes. Ongoing advancements have substantially enhanced battery performance, with energy capacity per price escalating over time. For instance, between 1991 and 2005, the energy capacity per dollar improved over tenfold, underlining the progression in battery technology. The evolution of lithium-ion batteries reflects a remarkable price reduction and enhanced energy density, with energy density more than tripling between 1991 and 2018, while prices plunged by nearly 97% in the same period. Innovations focusing on energy density enhancements, such as replacing graphite with silicon, show promise in achieving unprecedented battery energy densities and making electric vehicles more cost-competitive with internal combustion engines. Moreover, variations in energy density exist among cells of the same chemistry, but different sizes and formats, with factors like packing density and electrode thickness playing crucial roles. Round-trip efficiency evaluations provide insights into the energy utilization of lithium-ion cells, with experiments delineating the charge and discharge efficiencies under various conditions and C rates, showcasing the advancements in battery technology and efficiency optimization over the years. The lifespan of a lithium-ion battery is commonly referred to as the number of full charge-discharge cycles it undergoes before reaching a defined failure point in terms of capacity loss or impedance increase. Manufacturers indicate this lifespan as cycle life, denoting the number of cycles until the battery retains 80% of its rated capacity. Apart from cycling, simply leaving lithium-ion batteries in a charged state can diminish their capacity and elevate cell resistance, predominantly due to the continuous formation of the solid electrolyte interface on the anode. Calendar life encompasses the entirety of a battery's life, encompassing both active cycles and periods of inactive storage. Various stress factors such as temperature, discharge, charge currents, and state of charge ranges influence battery cycle life significantly. The degradation of batteries during storage is heavily impacted by temperature and state of charge, where exposure to high temperatures and full charges, 100% state of charge, can lead to substantial capacity reduction and gas production. Multiplying the cumulative discharge of a battery by its rated nominal voltage yields the total energy delivered throughout its life, facilitating calculations for energy cost per kilowatt hour, encompassing charging expenses. As batteries age, gradual degradation occurs, resulting in reduced cyclable charge and heightened resistance, leading to lower cell voltage during operation. Numerous degradation processes affect lithium-ion batteries, occurring during cycling, storage, and constantly throughout their usage. Temperature plays a crucial role in degradation, with higher temperatures accelerating degradation significantly, while room temperature offers the most favorable battery life conditions. High charge levels and extreme discharge levels can hasten capacity loss, while maintaining the battery within a moderate state of charge range of about 60% to 80% can mitigate capacity decline. Scientists have employed 3D imaging and model analysis to identify key causes and potential remedies for battery degradation over charge cycles, highlighting aspects like particle cracking and electrode reaction heterogeneity as significant contributors to degradation. Common degradation mechanisms in lithium-ion batteries encompass electrode material reduction, lithium metal plating, and structural degradation of cathode materials, leading to varying forms of capacity fade and increased resistance throughout cycles. The correlation between operational stress factors, aging mechanisms, and their effects on lithium-ion battery aging is essential in understanding the progression of degradation. Studies on battery aging typically involve elevated temperatures to accelerate aging processes, with different battery chemistries exhibiting varying degradation rates under these conditions. For instance, lithium-ion batteries with titanate anodes showcase extended cycle life due to the absence of solid electrolyte interface, SEI, growth compared to batteries with graphite anodes, highlighting the influence of anode material on battery longevity. Detailed mechanisms like the formation of SEI layers and lithium plating elucidate the intricate processes that occur within lithium-ion batteries, influencing their efficiency and overall lifespan. Mitigation strategies such as optimizing charging conditions and materials innovation aim to combat degradation mechanisms and enhance the performance and safety of lithium-ion batteries. Temperature control, electrolyte enhancements, and protective coatings are among the approaches utilized to mitigate issues like lithium plating and electrode material degradation, ensuring prolonged battery lifespan and operational efficiency. The safety concerns surrounding lithium-ion batteries have been acknowledged since their commercial debut in 1991. Issues leading to fires and explosions often stem from processes occurring at the negative electrode, cathode. Rapid charging or charging at low temperatures can cause lithium metal to plate on the anode, creating dendrites that may breach the battery separator, resulting in internal short circuits and subsequent overheating and ignition. Additionally, an explosive reaction between the anode material, Li-C6, and the solvent, liquid organic carbonate, can occur, especially when the anode temperature surpasses 70 degrees Celsius. To mitigate these risks, reputable manufacturers now incorporate dual safety mechanisms in all lithium-ion batteries larger than 18650 size, including a current interrupt device, CID, and a positive temperature coefficient device, PTC. The PTC is comprised of two metal discs that break electrical contact when pressure within the cell rises, halting the electric current. On the other hand, the CID features an electrically conducting polymer that increases resistance when exposed to high current, reducing the current flow through the battery. Due to their flammable electrolyte and potential pressurization when damaged, lithium-ion batteries pose safety hazards. Factors like poor cooling, overcharging, external short circuits, physical damage, and internal faults can lead to thermal abuse, electrical issues, or mechanical failures, culminating in fires or explosions. Notably, stringent testing standards are in place, surpassing those for acid electrolyte batteries, and additional safety measures are enforced by regulators for shipping. Instances such as the Samsung Galaxy Note 7 recall in 2016 underscore the importance of addressing battery safety concerns, especially given the potential risks associated with flammable electrolytes and faulty charging practices. Researchers are actively exploring non-flammable electrolytes to enhance battery safety and prevent hazardous incidents. Mismanagement of lithium-ion batteries, including damage, overloading, or improper disposal, can result in catastrophic outcomes like explosions or fires. External short circuits, especially from improper disposal practices, present significant risks. Proper disposal and recycling processes are crucial to avoiding incidents like fires in recycling facilities. Thermal runaway, a scenario where battery temperature increases uncontrollably, can lead to cell rupture or ignition. Fail-safe circuitry is incorporated in many lithium-ion cells to disconnect the battery during unsafe voltage ranges or charging conditions. Voltage stress beyond safe limits can accelerate battery aging and compromise safety. Strategies like using alternative positive electrodes such as lithium iron phosphate, LFP, have been adopted to enhance battery safety in critical applications like electric vehicles. Incidents like the Sony laptop battery recall in 2006 and airplane battery fires have spurred industry-wide efforts to enhance lithium-ion battery safety. Researchers continue to explore innovative solutions such as non-flammable electrolytes and alternative electrode materials to mitigate safety risks associated with lithium-ion battery usage. The electric vehicle supply chain involves mining, refining raw materials, and manufacturing batteries and components. In 2024, China dominated 60% of Li-ion battery production. During the 1990s, the USA was a top lithium miner worldwide, but Chile took over by 2010 with lithium brines in Salar de Atacama. By 2024, Australia and China also became leading lithium miners. Environmental impacts from lithium extraction, nickel, cobalt, and mining byproducts pose significant hazards to the ecosystem and human health. Water pollution, ecosystem degradation, and landscape damage are some consequences. Cobalt mining in the Congo leads to deforestation, while nickel mining causes environmental degradation in countries like the Philippines and Indonesia. Manufacturing 1 kg of Li-ion battery demands about 67 megajoules of energy. The global warming potential of lithium-ion batteries manufacturing varies based on the energy sources, estimating 73 kmol of CO2 CO2 in a 2019 study. Effective recycling significantly reduces the carbon footprint. Most Li-ion batteries are recycled with elements like iron, copper, nickel, and cobalt considered safe for disposal. Cobalt remains the most expensive metal in battery construction. Accumulation of battery waste poses technical challenges and health risks. Developing efficient ways to repurpose waste is crucial due to the environmental impact of electric cars heavily tied to lithium-ion battery production. Recycling processes involve storage, testing, disassembling, chemical separation of battery components, and pyrometallurgical or hydrometallurgical recovery methods.